Hey, agriculture enthusiasts, farmers, and tech-curious minds? Have you ever wondered how farmers can analyze the health of their crops from hundreds of miles away? Or how they make hyper-targeted decisions that save money and protect the environment? Today, we're diving deep into a groundbreaking technology that's revolutionizing farming, the Normalized Difference Vegetation Index, or NDVI. At its core, NDVI is a simple yet incredibly powerful measurement derived from multispectral remote sensing data. Think of it as a robust proxy for vegetation health, density, and how well plants are photosynthesizing. So, how does it work? It all comes down to light. Healthy plants full of chlorophyll are incredible at absorbing red light for photosynthesis. That's why they look green to our eyes, they reflect green light. But here's the magic. Healthy plant cells also strongly reflect near-infrared (NIR) light, which is invisible to us. When a plant is stressed, diseased, or lacking nutrients, its chlorophyll decreases, meaning it absorbs less red light. Its cellular structure also changes, leading to less NIR reflection. NDVI takes advantage of this stark contrast. It's a normalized ratio that quantifies the difference between NIR and red light reflection. The resulting value ranges from -1 to +1. High positive values, like 0.6 to 1.0, indicate dense, healthy vegetation. Lower positive values, 0.2 to 0.5, suggest sparse or stressed plants. Values near 0 or negative indicate bare soil, water, or non-vegetative surfaces. This normalization is crucial, as it helps account for varying light conditions and atmospheric effects, making the data incredibly consistent. So, how do we get these incredible spectral measurements? The data comes from various platforms, each with its own advantages. Satellites. These are the workhorses for large-scale monitoring. Platforms like Landsat and Sentinel-2 provide consistent, global imagery. Sentinel-2, for instance, gives us up to 10-meter resolution and revisits every 5 days, perfect for tracking seasonal trends across vast agricultural lands. They're great for the big picture. Unmanned aerial vehicles, UAVs. Drones. For ultra-high precision, drones are unmatched. Equipped with lightweight multispectral sensors, they can capture imagery down to the centimeter level. This means you can assess the health of individual trees in an orchard or pinpoint small patches of weeds. Drones offer incredible flexibility for on-demand targeted analysis. Handheld and tractor-mounted sensors. These are proximal sensors, meaning they're right next to the plants. Devices like the Trimble Green Seeker emit their own light, allowing for real-time on-the-go measurements. Their primary use? Immediate tactical decisions like variable rate nitrogen fertilization as a tractor moves across the field. It's important to note that while these platforms provide NDVI data, the measurements can differ slightly due to viewing angles and resolution. Consistency in sensor use is key for accurate decision-making. NDVI isn't just a cool scientific metric, it's a fundamental tool in modern precision agriculture. It provides the foundational data for strategies that optimize inputs, enhance sustainability, and improve profitability. In-season crop health and vigor assessment. NDVI maps are typically color-coded dark green for healthy, dense vegetation, yellow for moderate stress, and red for bare soil or severe stress. This intuitive visual transforms complex data into an easy-to-understand bird's-eye view of your fields. It instantly highlights spatial variability that would be impossible to see from the ground. Early detection of biotic and abiotic stress. This is one of NDVI's superpowers. Plants change their spectral reflectance as soon as they're impacted by stress, often days or even weeks before visual symptoms like yellowing or wilting appear. A sudden drop in NDVI in a specific area can be an early warning signal for nutrient deficiencies, especially nitrogen, water stress, pest infestations, or diseases. This early detection allows for proactive management, preventing minor issues from becoming major disasters. Informing variable rate application (VRA) strategies. This is where NDVI truly shines for efficiency. Instead of applying a uniform rate of fertilizer, pesticides, or water across an entire field, VRA tailors applications to specific management zones identified by NDVI. You generate an NDVI map, delineate zones, create a prescription map with specific application rates for each zone, and then load it into your GPS-enabled farm machinery. This ensures resources are allocated precisely where needed, optimizing costs and reducing environmental impact. Biomass estimation and yield forecasting models. There's a strong correlation between NDVI values measured during critical growth stages and final yield. Higher NDVI generally means greater biomass and higher production. By analyzing historical NDVI data and actual yields, ag tech companies can build models to estimate future yields, helping farmers plan marketing strategies, harvest logistics and storage, and even aiding regional food security forecasts. Orchard systems, with their perennial woody crops and complex, multi-layered canopies, present unique opportunities and challenges for remote sensing. NDVI is a valuable tool, but its limitations here are particularly important to understand. Assessing individual tree health and canopy vigor. High-resolution NDVI imagery, often from drones, allows growers to assess the vigor of each individual tree. NDVI acts as a proxy for canopy density, leaf area, and overall photosynthetic activity. It helps monitor vegetative development, compare performance between blocks or varieties, and identify trees showing signs of stress. Identifying spatial variability for management zones. Just like in row crops, orchards have significant variability due to soil type, topography, or irrigation. NDVI maps clearly reveal these patterns, pointing to chronic issues like poor drainage or compaction. This spatial information is crucial for site-specific management. Targeted scouting to diagnose specific stressors. Variable rate nutrition, applying fertilizers only to underperforming zones. Adjusting irrigation schedules based on water needs. Even creating stratified sampling plans for more accurate yield estimation with fewer samples. Case studies. Research consistently validates NDVI's utility. In apple orchards, NDVI has been used to predict yield variability. For citrus greening disease, NDVI helps detect infected trees, though other indices show even greater sensitivity. In sweet cherry orchards, NDVI is a reliable indicator of water stress. The challenge of signal saturation. This is NDVI's Achilles heel in mature orchards. As a canopy becomes very dense, NDVI values approach a maximum of +10. At this point, the index saturates and loses sensitivity. It can't differentiate subtle changes in chlorophyll content or nitrogen status within an already healthy, dense canopy. The red light used in the calculation is absorbed by the top layer of leaves, masking the health of lower shaded leaves. By the time stress affects the top canopy and NDVI drops, damage might already be irreversible. This means NDVI is most effective for identifying relative health and spatial variability in dense canopies, guiding where to scout, but less so for precise quantitative assessments. This limitation has spurred the development of more advanced indices.